So we will start talking about derivatives today again, because we started on Wednesday. Today we're going to talk about functions, about derivative functions in a little bit more abstract terms, and I'm going to give you a few more examples. And did you have any questions from last time, from last lecture? No questions? Okay, great. Who can tell me what the derivative was in your own words? Yes?
It's the slope of the tangent line at a certain point.
Okay, it's the slope of the tangent line at a certain point. Very good. The slope of the tangent line of what? Of a function, right? Right. So I give you a function and I give you a point, and you can draw the tangent line at that point. And the slope of that is the derivative. So you draw a function, f of x. You take a point, let's call the point A. You draw the tangent line at that point, and the slope of that is the derivative of the function at the point A. So f prime of A is the slope of, let's just to make it a little bit shorter, the slope of f at the point A using tangent lines. So the method to figure out the slope of the function is by drawing a tangent line at that point. Okay, we are going to use a slightly different notation today, because we want to be able to talk about f prime of x. You guys most of the time have probably seen if f of x is such and such function, then f prime of x is this other function. You don't want to change the variable when you talk about the derivative. So we will slightly change the notation and say that for any x real number, f prime of x. And then what we're going to do is we're going to consider, let me do a drawing here just so you see it. So this is the point x. This is the point x plus some increase that I'm going to call h. I'm going to make a line that goes from this point to this point, like this. And I'm going to draw this triangle, the same triangle as before, to calculate the slope of the function at that point. Now, using that notation, if I have x and x plus h instead of what we had before, what would be the thickness of this, or the length of this line over here? What do you think? This is x and this is x plus h. What is this? It's h, right? Okay, what about this vertical line over here? Well, it's a long line all the way from here to here, which is f of x plus h, right? Minus the shorter line, this line right here. Do you agree? Right, so this tall line is f evaluated at x plus h. The shorter line is f evaluated at x. So it's a subtraction between the two. So what is it that, what is the limit that we're considering now? What is the variable for the limit? Is it x? Now it's h, that's right. So now we are talking about the limit as h goes to 0 of, once again, the slope of the function. In this case, it's f of x plus h minus f of x divided by h. Okay, so it's the same story, basically the same thing with slightly different notation that allows us to talk about the function f prime of x instead of f prime of a. And that's the one that we're going to be using, I guess, from now on, because that's a more that's a more natural thing to do, to talk about x as the variable instead of a. Okay, let me give you an example using that notation to compute the derivative of a function. Also, I think in the past, yeah, we go back like one lecture, we're talking about derivatives. So in the past, we've done the derivative at a particular point. We said calculate the derivative at the point 2. So now we're going to go one step beyond that, and we're going to ask, what is the derivative at the point x in general? Okay, so you should realize that's a more abstract question, right? I'm not giving you a point. I'm telling you just, here's a point x, find a derivative at the point x. So I'm going to give you a function, f of x equals, let's see, 2 square root of x plus 1. And what we're going to do is we're going to find f prime of x in general for any point x. So we're going to use this definition. F prime of x is equal to the limit when h goes to 0. And now let's write the function. So this is f evaluated at the point x plus h. So what is f of x plus h in this case? Well, it will be 2 square root of, right? So think about a function again as a machine. F of anything is 2 times anything plus 1, right? So f of x plus h is 2 square root of x plus h plus 1. Okay, minus f of x. Okay, should I write here plus 1? Because it's the definition of f of x is 2 square root of x plus 1. What do you think? Plus 1? Minus 1, that's right. That's a common mistake, right? If you're writing minus f of x, you're writing minus the whole thing. So you should write a minus here and a minus here. Okay? Divided by h. Great. Okay, let's calculate that limit. What do you think cancels out first? Well, the 1 cancels out, right? So this one goes away with this one. And we have the limit, h goes to 0. And let's factor out that 2 and bring it over to this side here. Minus square root of x divided by h. Okay, now we're going to start seeing a payoff from all that drill that we did before. What do you think we should do at this point if we want to calculate that limit? The thing on the bottom goes to 0, right? The thing on the top goes to also 0 because it's square root of x minus square root of x. So that means we have to rephrase. Okay, what is the one? I mean, we've used like 2 tricks all the time repeatedly. So which one of the very few tricks that we've learned should we use in this case? Multiply by the conjugate. That's right. So multiply by the conjugate of this expression, which is square root of x plus h plus square root of x. On the top and on the bottom, right? Great. When we multiply by that thing, we get 2 times. And then, of course, on the top, we get a minus b times a plus b is equal to a squared minus b squared, which is x plus h minus x. And in the bottom, we get h times square root of x plus h minus square root of x. Oh, sorry, plus. Okay, so now there should be a few things that cancel out, and sure enough they do. You can see here the x cancels out with this x over here. Okay, so this x disappears. We end up with just an h on the top. Do you see anything else canceling out? Well, yeah, the h on the top cancels out with the h on the bottom. Very convenient, right? So this is the same as the limit when h goes to 0 of 2, 1 over square root of x plus h plus square root of x. Right. Is that clear? I did 2 steps at once. They're pretty easy. So what happens with that expression now? The top goes to 1. The bottom goes to square root of x plus square root of x. Right? So that is, this top goes to 1. The bottom goes to 2 square root of x. So this is equal to 2 times 1 divided by 2 square root of x. And that's 1 over square root of x. Okay? Awesome. Now, let me point something out that's kind of interesting in this function. What is the domain of f? What is the domain of the function f? What do you think?
I'm sorry, what's the question again?
What is the domain of the function f? That function.
Oh, that function?
Yes.
Let's see.
What are the values of x that I can plug into this expression?
Oh.
Can I plug in any negative numbers? Yes? All the positive numbers? Okay. Do I include 0 or not? 0. Including 0, right? Does the square root of 0 exist? Yes. That's fine. So the domain of the function f is all the points x bigger or equal than 0. We can write this as the interval from 0 to infinity. Now, what is the domain of f prime? So now you look at this function over here. F prime is 1 over square root of x. What's the domain of that? Does 1 over square root of 0 exist? No, right? Exactly. It would be all positive numbers, which one can also write as 0 to infinity using a round bracket. Okay. Now, I would like to ask you guys, why do you think that the derivative does not exist at 0? If the function exists at 0, there should be some intuitive reason for that. Well, here's what happens. If we drew the function, I'm going to draw the function f. It's going to be like the square root function, but multiplied by 2 and then transferred up, right? So that's going to look like this. What happens with the tangent line at 0?
There's no line to use. Just one point.
No, but you can draw the tangent. You know, you can still, right?
One point. You can't really.
Sorry? The tangent is vertical. That's right. So, Eric, right?
Yeah.
Eric points out that we don't really have a function defined on both sides. We really only have a function defined on one side, so it's harder to draw the tangent. But even if it's only defined on one side, you can still look at the points that are bigger than 0 and kind of draw a tangent, right? But even if you did that, right? Yeah. Even if you did that, you would have a vertical line. Vertical lines would have slope what? Infinity, right? Infinity. So this would be a vertical tangent at x equals 0, which is the reason why the function does not have a derivative at 0, because the slope would be infinitely large. Okay. Questions? Is that clear how we did the derivative of this function? You can do the exact same thing for any other function. Hypothetically, you know, if you were asked about it in an exam or something like that, right? Yeah, you don't think it's funny? I don't know. Okay, so notation. So turns out that there's multiple different ways of writing a derivative. In fact, it's a bit of a mess. It's like you're reading a Russian novel, right? and you're reading about this guy called Ivan and another guy called Vanya, and halfway through the book turns out they're the same guy. They're just two different ways of calling it, right? So in the same way, we're going to be using different notations for the same thing. The derivative of the function, okay, let's say that we have the function y equals f of x. The derivative of the function can also sometimes be called y prime of x, or just simply y prime. But it gets worse. Sometimes we're going to also call this dy divided by dx. Okay, what is its meaning of dy dx? Well, you might be tempted to think that it's a ratio, and I would recommend against it. It's not a ratio. Just think about it as just a notation. I'm going to tell you in a moment where the notation comes from, because there really is a meaning to it, and there's a reasonable justification for that. If you thought that, remember that last time we talked that we said that 300 years ago Newton and Leibniz got into a fight? So if you thought that fight was over, think again. Turns out that one of those notations was introduced by Newton and the other by Leibniz. And we're still using them over 300 years later. So this is Newton, and this is Leibniz. Okay, we're not using both just because we have two camps, and some people really insist on Newton's being right and the other guys insisting on Leibniz being right. We use two different notations because the two of them have their own advantages. Sometimes one of them is better than the other, and you'll see why when we start using them. For example, if I want to use this notation, which is really the preferable one, this is the one that I like the most, I first have to define what f is. For example, I have to say, let's say that f of x is sine of x, and then I can talk about f prime of x. With this notation, you can define the function and talk about the derivative at once. You could, for example, say dx of the function sine of x, or whatever it is. So you don't need to have two lines, one defining the function and one defining the derivative. You can write d dx of the function. And then just one more. Sometimes we will talk about df of x, just to make it, just for good measure, right? If there wasn't enough notation for it. So the bottom line is that 350 years later, people have still not really made up their minds how they want to call the derivatives. But really, there are some notations that are better than others for different situations. So no matter the notation, what should be clear to you guys is, my suggestion is to think of two different things. Make sure you understand what function it is that you're derivating. So if you look at an expression using some funny notation, think in your heads, think what function is it that I'm looking at, no matter what notation you're using. And second, at what point am I calculating the derivative? Okay? So what function am I talking about, and what point is it that I'm calculating the slope? Let me give you a few examples of this, or just an example. So as I said, we can talk about the function y is equal to, let's say, x squared plus 2. And then at that point you can talk about, well, okay, let's say that this is f of x. And then at that point you can talk about y prime of x, y prime of 2, or 3, whatever. You can ask about the derivative at the point 3. So if I write this and then I write y prime of 3, then what do you think, what function I'm talking about? You have to go back, right? You have to think about, okay, is the function f of x equals x squared plus 2, derivative evaluated at 3, okay? I can also talk about f prime of 2, and so on and so forth. So it's pretty clear. You can also talk about dy dx, meaning that's the derivative in general. But you cannot talk about the derivative d dx of the function x squared plus 2. How is that better than what we had before? Because you can write everything compactly in just one line. You can talk about the derivative of the function x squared plus 2. No need for 2 lines. Okay? What else? Let's see. Okay, so what about if you wanted to evaluate, so here's a tricky one. So you have this notation here, and you want to evaluate the derivative of this function at the point 2. Then what do? Should I say d dx of 2 squared plus 2? No. No, because then I would change, that's where I'm writing the function, right? If I just write 2 squared plus 2, that's a constant. The derivative is going to be totally different. So what I do is you sometimes write dy dx evaluated at the point x equals 2. Okay, so that way you know what function it is and at what point. Or I guess you can also say d dx of the function x squared plus 2 evaluated at x equals 2. So you know again what function at what point. So you see the notation can get a little bit messy, but if you think about it, it's really the same thing over and over again. Okay, questions? No? Okay. I'm going to justify a little bit this notation dy dx. So I'm going to draw back the same thing as I was drawing before. Let's say that you have a point x, you have another point, and you have this triangle here. Okay, so you can think about this small increase. We were calling it h, but let's think about this small increase as delta x. This, the little triangle is a delta. And you can think about delta x as a small increase. Basically what we were calling h is the same thing. And so in that case, the bottom thing is delta x. And we can think about this vertical line as delta y. So it is the increase in x versus the increase in y. Okay? And as the increase in x becomes smaller and smaller, you converge towards the derivative. So dy dx is equal to the limit as the increase becomes smaller and smaller of delta y divided by delta x. So that is the reason why Leibniz, way back when, decided to use this notation dy dx, because the d is supposed to be some kind of like very, very, very small increase. For example, dx is supposed to be an infinitesimally small increase in x, and dy is supposed to be the infinitesimally small increase in y. It's not clear what you mean by infinitesimally small increase, because if the increase is 0, then it's no increase at all, right? Which is why the calculus didn't make a lot of sense for several hundred years. You had to be really smart to make sense of it, and people waved hands a lot, talking about infinitesimal increases here and there. And it wasn't until the 19th century, actually, with the work of some French guys like Cauchy and some German guys like Weierstrass, that the whole thing started to make more sense. What those guys in the 19th century did was to introduce the idea of the limit that didn't really exist before. Okay, so more about history. Anyway, so where was I? Yeah, okay, notation. So we're done with the notation. Questions about notation? Okay, great. So now let me ask you again. We were talking about this function that had this this funny property that the derivative did not exist at one point. There was some vertical tangent, so therefore the derivative doesn't exist there. So this kind of brings up the question, where do derivatives exist? How do I know if the derivative exists? Do they always exist? So when does f prime of x exist. As you can see, it doesn't exist always. Sometimes it doesn't. So we will talk about, we will introduce a definition to say when a function has a derivative. We say that f is differentiable at a or at x, at a if f prime of a exists. And by that, of course, I mean that the limit, this limit over here exists. Sometimes the limits don't exist, right? So if the limit is d and e or does not exist or something like that, then we say that the function is not differentiable at a. And we also say that f is differentiable at an interval ab. Remember, this is an interval notation. This is all the points that are lying between a and b. We say that a function is differentiable at an interval, or even just differentiable in general, meaning that it's differentiable at every point in the interval. If it is let me write it like this. If f prime of x exists for every x element of AB. Okay, now some people were asking me in the office hour that they were confused over the sign. So I'm just going to stress it just so everybody knows. This means what? So x e AB means that x is an element of the set AB, which is maybe a fancy way of saying that x is a real number that lies between a and b. Okay? So it's a set notation. Maybe some of you have not seen it before, so I'm just going to stress it here. But it literally just means any point between a and b. Okay? So what does it mean that f is differentiable at any point between a and b? Well, you grab any point, you draw the tangent, and the tangent is a well-defined, the slope is a well-defined limit, then the function is differentiable. So I keep waving my hands around what it means to be differentiable. So let me give you a few more examples about when the function is not differentiable. For example, who can give me an example of a function that is not differentiable? Yes? Okay, very good. The absolute value of x has a corner. So let me do a little bit more abstract version of that. Suppose that the function f of x looks like this, and the point A is down here. So what if I wanted to calculate the derivative of the function at the point A? What do you think would happen? Sorry? Too nice? What do you mean too nice? No, it's good. Well, any other comments? What happens? Yes? It would form a vertical line, maybe. Yeah, I mean, you could, I don't know. Sure, you could, yeah. I guess you're thinking about the previous example, right? The example with, maybe you're thinking like this, like a vertical derivative. But let's say that this is not vertical. This is just a corner, It's not a vertical slope. For example, the function absolute value of x. Do we, in that case, have a derivative? Well, we don't. And the reason is that we really don't have a single choice for the tangent. We can draw several tangent lines that are equally valid. Okay? because there's not a well-defined tangent line, there's not a well-defined slope. Okay? So that means that the derivative is not defined at A. So f prime of A does not exist. What else could happen? Well, you could have a function that is not continuous at A. Okay, so what do you think happens in that case? Well, once again, we don't have a well-defined tangent. There's no way to just draw one nice tangent line that touches the function just at one point. In fact, you could think about doing two tangents, one over here and maybe one over there. But they might have two different values. So once again, there's really not a single choice of the tangent. So this is a f not continuous f prime of A does not exist. And finally, we can think about a case like the one before and like the one I think you were thinking about, where the function has a vertical tangent. So this is, once again, f prime of A does not exist because there's a vertical tangent. These are just a few things that can happen and that mean that the function is not differentiable at the point A. All right. Okay. Questions? All right, so let's oh yes, question, sorry.
Would like
Manriquez.
another one be the cusp, like another one that the derivative wouldn't exist.
Okay, what do you mean by a cusp? Is that the same as a corner or?
It's like similar to like a corner, but I think it's kind of like a curve, something like that, like doesn't exist.
But different from this?
Yeah, it's different than the corner, like a little different.
Okay.
Yeah.
Maybe. Yeah, I don't really know what you mean by a cusp, but yeah, that's certainly possible that you can have a funny looking shape that the tangent is not well defined. So the function does not have a derivative there. Okay. Now, what else? Well, as it turns out, once you calculate the derivative of a function, you can keep going. You can take the derivative of the derivative. Okay? Because you see the derivative is a function just like f. So you can take f and you can take the derivative of that. And that leads us to what we call higher order derivatives. Okay? So just like f prime of x is the derivative of f of x, we can write f prime prime of x. Okay? It looks like it's going to be very messy to write, but actually it's not. It's actually fairly reasonable. You can think about f prime prime of x as being simply the derivative of the function f prime of x. Okay, so you got a function, you derivate it, you get f prime, derivate it again. You can also talk about the third derivative. This is second derivative, third derivative, and so on and so forth. Okay, let me give you an example of this. Here's 1, 2, and 3. 1, 2, and 3. And I'm going to draw a function. Let's see. Like this. Something like this. This would be my function f of x. Notice that it has slope. What is the slope at 1? It's more or less minus 1, right? And what is the slope at 3? It's more or less 1, right? Awesome. So I think we've done this before. No, I don't think we have done it before. So the derivative at 1 is minus 1. The derivative at 3 is more or less 1. What is the derivative at 2? It's more or less 0, right? So I can go ahead and draw the function f prime of x on the graph itself. So you see the derivative at 1 was more or less minus 1. The derivative at 0 was more or less 0. I'm sorry, at 2 was more or less 0. The derivative at 3 was more or less 1. So I can calculate the derivative at every point, and I get something like this. F prime of x. Okay? Do you agree? All right. But now I take that function, and I want to derivate that. So forget about f for the moment. Let's look at this red function by itself, or this function down here by itself. What do you think is the derivative at 2, more or less?
Wouldn't this be 1?
It seems to be more or less 1. And the derivative here is also more or less 1, and over here is also more or less 1. So the function is more or less, that second derivative is more or less equal to 1 all over the place. So this is f prime prime of x. All right. So there you go. That's graphically the relationship between the function, the derivative, and its derivative, second derivative. Okay, let me give you another example. If f of t is the position function at time t, then the derivative of that function actually has a name of its own. What was that?
Velocity.
Yeah, that's right. We call this the velocity. Okay? The rate of change of the function. What about the second derivative?
Acceleration.
That thing also has a name, and it's the acceleration. What about f prime prime prime? Yeah, I don't know about that one either. I think it has a name, but I don't know. All right, so great. So as you can see, the second derivative is a common, well-known concept in many functions. Let me do an example that is an algebraic example, and then we'll finish. F of x equals to x squared plus 2. And we want to find f prime of x and f prime prime of x. So let's start with f prime. It's the same story as before. Is the limit as h goes to 0 of, and then we write x of h plus x minus, well, let me just write it down again. F of x plus h minus f of x divided by h. And that's going to be f of x plus h is going to be x plus h squared plus 2, right? Okay, I'm just going to write in one step. I'm going to factor out, write that as x squared plus 2xh plus h squared plus 2. That whole thing is f of x plus h minus f of x divided by h. Great. So there's a bunch of stuff that cancels out. The 2 cancels out with the 2. This x squared cancels out with this x squared. And I get limit when h goes to 0 of 2xh plus h squared divided by h. But once again, you can cancel some stuff out. You can factor out h. This is 2x plus 1 plus h divided by 1. Okay? And what's the limit of that? Eva, what's the limit? 2x, that's right. Okay, great. So we know that f prime of x is equal to 2x. Great. Awesome. Now, we can do the same procedure to find out the second derivative from the first derivative. So that's what's new in this example, is that f prime prime of x is equal to the limit as h goes to 0 of the function f prime of x plus h minus f prime of x. Notice that I'm writing f prime instead of f, because now we're taking the derivative of f prime, right? This is divided by h. So this is 2x plus h minus 2x divided by h. And the 2x cancels with this 2x over here, so I get 2h over h. Right? Because this is 2x plus 2h minus 2x. And I can cancel out the h on top of the bottom. And that's equal to 2. So the second derivative is just 2. Great. So I believe because this chapter, this section fits in nicely with what we talked about on Wednesday, and there's really not that much that's new, I would say that the exam goes all the way up to today. Okay, so the material for the exam will be all the way up to today, including today. On Monday, we'll talk about just functions in general and derivatives in general. We're going to do a review of the material, and on Wednesday, we'll have the exam. Okay, do you have any questions? No questions, okay.